Welcome to this explainer, where we're going to break down the modern database landscape and guide you through the evolution from one-size-fits-all storage straight into polyglot persistence. Look, if you're building or scaling modern apps today, understanding exactly how and where your data lives is, without a doubt, the absolute most critical architectural decision you can make. So today, we're going to visually map out exactly why the database world split, how it evolved, and, most importantly, how to choose the right tool for the job. Okay, here's our agenda for today. We're covering 1. The big data explosion, 2. SQL, the relational standard, 3. NoSQL, flexible and scalable, 4. 4 flavors of NoSQL, 5. Acid versus cap theorem, and finally, 6. Choosing your data model. Let's get right into it.
Section 1. The big data explosion.
2.5 quintillion. Just pause and think about that massive number for a second. That right there represents the bytes of data generated globally every single day. It's staggering, and it establishes exactly why our traditional data architecture had to evolve. You know, back in the 1970s when storage was crazy expensive, the main goal was just reducing duplication. But today the goal is handling absolute data avalanches efficiently. But hey, the real challenge isn't just the sheer size of the data. It's the totally messy, unstructured nature of things like social media feeds, smart sensors, mobile app logs, and video files. This kind of data just doesn't fit neatly into traditional rows and columns. In fact, if you try to force it into a strict grid, you are looking at a recipe for massive performance bottlenecks and development nightmares. Section 2. SQL, the relational standard. For decades, structured query language, or SQL, has been the undisputed heavyweight champ. Relational database management systems basically organize structured data into highly predictable related tables. Think of an e-commerce platform, right? You've got one table for customer info and another for orders. They share a unique ID, a key, that links them perfectly together. It's incredibly logical, highly structured, and it's just perfect for predictable data sets. And this strict structure is exactly why institutions like banks absolutely rely on SQL. It requires data to be perfectly structured before saving it, which is a concept we call schema on write. Basically, if a piece of data is missing a required field, the database just rejects it entirely. This guarantees absolute data integrity. Plus, traditional SQL scales up vertically. So if your database needs more power, you just migrate to a larger server, bolting on more CPU, more RAM, or a bigger hard drive to that one single machine. Section 3. NoSQL, flexible and scalable. As we've seen, not all data fits perfectly into a rigid spreadsheet model. And that brings us to the challengers that emerged in the early 2000s. NoSQL shifted the entire paradigm by trading strict tabular relationships for the ability to just ingest raw, unstructured data in its native format. Often called not only SQL, it was built specifically for modern apps that need to move fast, iterate quickly, and handle data that constantly changes shape, all without having to rewrite the whole database structure every single time. When we put the two paradigms head-to-head, a crucial difference really pops out. We know SQL relies on vertical scaling and rigid rules. NoSQL, on the flip side, scales horizontally. Instead of buying one massive, super expensive server, you distribute your NoSQL database across a bunch of smaller, cheaper servers, or nodes, working together in a cluster. This gives you near limitless scaling and dynamic, flexible schemas that could actually adapt as your app evolves. Section 4. 4 flavors of NoSQL. Now, unlike SQL, which pretty much looks the same everywhere with its tables, rows, and columns, NoSQL is actually an umbrella term for 4 completely different ways to model data. We're going to run through these primary formats real quick because understanding the difference between them is basically the secret to unlocking high-performance architecture. First up, we have key value stores like Redis or DynamoDB. Think of this like a massive, highly efficient dictionary. You have a unique key, and it points directly to a specific value. Because it's so incredibly simple, it is blindingly fast. This makes it the absolute perfect choice for things that demand microsecond response times, stuff like user session caching, gaming leaderboards, or keeping track of what's in a shopping cart. Next on the list are document databases, like MongoDB or Couchbase. Instead of shattering a user profile across a dozen different tables, document databases let you store complex, evolving records in a single, flexible, JSON-like object. It maps beautifully to how developers actually write application code today, which makes it super popular for product catalogs, content management, and complex user profiles. The third flavor is the column family store. sometimes called a wide column database, like Cassandra or HBase. This model organizes data into columns rather than rows. If you need to ingest massive, continuous streams of data, like telemetry from millions of Internet of Things sensors or endless application log files, column family stores provide near-boundless horizontal scale and incredibly high write throughput. And finally, graph databases like Neo4j or Amazon Neptune bypass traditional tables entirely. They map out data using nodes, representing things like people or places, and edges, which represent the relationships between them. If you're building a recommendation engine, a complex social network, or a fraud detection system where you have to quickly traverse deep webs of interconnected data, the graph database is definitely your ultimate tool. Section 5, Acid versus Captive. But choosing between these paradigms isn't just about the shape of your data. It's really about fundamental computer science theory and the trade-offs you have to make in a distributed system. SQL databases basically live and die by ACID compliance. That's a set of strict properties guaranteeing a transaction is processed reliably, like if you transfer money between bank accounts. Atomicity ensures the entire transaction completes, or it all fails together. It's never going to leave your money just lost in the ether. Relational databases absolutely excel at the strict transactional integrity. On the other hand, distributed NoSQL databases operate under the CAP theorem. This theorem states that in any distributed network, you can only guarantee 2 out of 3 traits at any given time: consistency, availability, or partition tolerance, which basically means the system survives network dropouts. Since distributed systems absolutely have to tolerate partitions, NoSQL databases usually force you to trade off between immediate consistency and high availability. Basically, sometimes getting a super fast response is just more important than getting the most perfectly updated response.
Section 6, choosing your data model.
So how do we actually translate all this underlying theory into an actionable framework for your architecture? Well, you have to map the database to the specific workload, and the answer here is polyglot persistence. You wouldn't use a graph database to process a highly regulated financial transaction, just like you wouldn't use a strict SQL database to temporarily cache high-speed user sessions, right? You look at the data shape, the required latency, the scale, and you pick the precise tool for the job. As the Azure architecture documentation explicitly reminds us, the goal isn't to pick a single winner in some imaginary database war. The true secret to modern system design is strategically combining these models, where data lifecycles and access patterns clearly diverge. It is perfectly normal and actually recommended to have a SQL database handling your billing while a NoSQL document database seamlessly runs your product catalog. I want to leave you with this final thought as you evaluate your own tech stack. Are you forcing unstructured data into a rigid SQL table just because it's what you're familiar with? Or are you really embracing the power of polyglot persistence? Because making the strategic choice here and matching the exact right data model to your unique workload, well, that could be the difference between a system that scales globally and one that just grinds to a halt under its own weight.